Welcome to this lecture series in linear algebra. In this lecture, we'll look at linear maps and their interactions with subspaces. And let us recall what we need to know. So more or less, we just need to know the definition of a linear map. So if V and W are vector spaces over a field S, so both of these vector spaces are over the same field F, then a map from V to W is called a linear map if these two conditions hold. Let me not expand on that. So that's the definition of a linear map, and both of these can be written in one shot equivalently to say that T alpha x plus beta y is equal to that for all. Right, I failed to emphasize this in the last video, but I'm sure you realized it. And more generally, if this is a linear map, then this holds. So what we are saying for two vectors x and y actually can be said for n vectors, and that is actually just a simple consequence of this and induction, if you want to be completely formal. Okay, here are some problems for practice. And now let us get started. So suppose we have a linear map, which means implicitly that V and W are both vector spaces over a same or a common base field. So we have a linear map. We define the kernel of T as those things in the domain that get killed by T. That is the definition of the kernel of T. This is called the kernel. Okay. And you may note that this is same as the preimage of 0 under T. Okay. And we have this image of T. This is nothing new. This is just the image of the map T. Purely set theoretic concept. Can also be written as T of V. Okay, so these are two notions that we associate to any linear map. And interestingly, kernel of T is a subspace of V. Whenever you have a linear map from V to some other vector space, of course, they have to be over the same base field, then the kernel of that linear map will be a subspace of the parent or the domain space. Proof is very simple. One just needs to check the addition and scaling property, meaning that kernel of T is closed under addition and closed under scaling. Let me check closed under addition, and closed under scaling can be left as an exercise. So let V, let's say x and y rather, are in kernel of T. Then what about x plus y? By linearity, we have this. But since x and y are in the kernel, tx and ty are 0. So this is 0 plus 0, which is 0. Which implies, basically this is the upshot, that this thing is 0, which implies x plus y is in the kernel. So this shows closure under addition. Similarly, you can show closure under scaling. And that finishes the proof. And similarly, image T is also a subspace, but of course, this will be a subspace of the target. And this is also very easy. Let me do the addition part. So let's say, what notation is good? Let me stick to x and y, although that can be confusing. So suppose x and y are in the image of T. Then we can find two vectors in the domain such that this is by definition of image. If two things are in the image, they are the images of some things in the domain. So that's just a matter of definition. Therefore, x plus y is tu plus tv, but now use linearity to write this, which implies x plus y is also in the image of T. And that shows closure under addition. One can similarly show closure under scaling. Fine, so these two are subspaces. One last thing that we want to show is an interesting property again. So we have a linear map from V to W, and U is a subspace of the target space. Then the preimage of U under T is also a subspace of V. So what is preimage of U? First of all, let me just clarify what that is. It's a purely theoretic notion. Those vectors in the parent space such that their images lie in U. Right, so we want to show that this is a subspace, but before we do that, note that this is a generalization of the fact that kernel is always a subspace, because kernels are nothing but preimages of the trivial subspace, namely the zero, the singleton zero. So this generalizes the fact that kernels are subspaces. Anyway, so the proof again is very, very simple. We'll just do closure under addition. So let's say x and y are in the preimage of U. Then tx and ty are in U by definition of preimage. That implies, by virtue of the fact that U is a subspace, the sum of tx and ty will also be in U, and therefore by linearity of T, this happens, and hence this happens. So this shows closure under addition, and closure under scaling can be left as an exercise now. So very simple, but these are also very important things. With that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.